it says here only you have one attempt until the deadline.
So I got only one chance.
Yes.
Oh, so scared. Thank you.
No need to be scared. It's open book, so you can look up information. Just do not talk to neighbors, please. I mean, or any. Okay?
Okay.
So do it yourself. No problem. No need to be scared.
Okay.
Okay, let's give it another 2 minutes until it's really 1:10. All right, it's 1:10. Good afternoon, everybody. We've got 16 students present. Maybe we'll have a few more joining us very soon. Well, this is a relatively small course, partially apparently because of an overlap. Yeah, let's see. And this will be recorded. Let me press the record button. Go to the cloud. All right, so from now on, everything will be recorded. This includes the chat. All right, you should be able to see the front page. I just want to remind you of what's happening this week. Obviously, we've had the first lecture, general introduction lecture on Monday. Today is exciting, I think. Well, I'm a little bit biased because I'm the lecturer. Today is exciting because we'll go through, well, search-based option engineering. We'll have an introduction to this today. If you want to learn more, read more, there's a lot of material here. There's a short video, somewhat short video by Mark. Here, for those who are overseas or who cannot access YouTube, let me know. Maybe I can make it work somewhat differently. Yeah, but there's definitely enough in there if you want to read up on it, go through his paper. In general, please do not pay for these scientific articles. Yeah, no need to. Look up how to connect via VPN to the University of Adelaide network, and then you can access all the papers for free. Yeah, do not pay for any articles. If it's, yeah, simply don't. Please don't. Cool. All right. One administration creative thing is videos, as I briefly mentioned, are by default deactivated. You are, however, most welcome to turn on your video camera just to say hi or just to show yourself for a while. Either is fine. It's not mandatory. If you want to to ask something during the lecture, please do so via the chat. I'm keeping my eyes here on the chat window. I have it on a different screen, and if I miss it, I'll tend to it at the very end of the lecture, definitely. Yeah. Nantian has a question already about quiz 1. Quiz 1 should finish after this course today, so after today's lecture. There's nothing to mention on Monday. Not entirely sure. Well, the quiz 0 and quizzes 1, they should both have deadlines on, let's go double check, on March 5th. Today's March 3rd, so you still have 2 more days. So it's plenty of time. I think filling out each quiz takes about 5 minutes in total. Yeah, just do it at your leisure. Cool. Without further ado, let's get started. And in particular, let's get started here with this little exercise. Just a quick check on you. Can you please open onlineclicker.org? I'll show you what it looks like. Onlineclicker.org. Apologies. So you can, for those of you who dial in from overseas, you can access this, to the best of my knowledge, from China as well. Then type in the phone number, 8000, say vote, and then did you start with the individual assignment 1? 1 for yes, 2 for no. Click 1 if you have started, click 2 if you have not started. So please do this, just to give me an idea, okay, how many of you have already worked with this. There's no need to create any account. Just visit this website, go to poll 8000 and go for 1 for yes and no for 2. I'll give everybody, say, another 20 seconds from now on.
Marcus, I'm sorry to interrupt. What is this poll for? I didn't capture that.
I would like to see whether you have started with the assignment 1.
Okay, understood. Okay.
Sorry, I should have probably said this. No responses to date. Who has started, who has not started? What is the poll number? Poll number is 8000. Oh, 8000. You should be able, am I not sharing my screen here? How do we vote? You just click on you type in the 8000, and 1 is yes. I have the feeling that you can't see my screen, can you?
Now we do see your screen. Earlier it was not visible. Yeah.
Okay, but you do see the PowerPoint, right? Just double check.
Yeah.
Okay. So the entire, Sayoni, you were saying we can see the entire home screen. You see just the PowerPoint, or you see several home screens? Because I have a 2 monitor setup. And on the 8000.
We see the entire screen, like the PowerPoint, the online clicker.
Okay, you see the entire
Zoom participants. Yeah, your desktop, everything.
Oh, okay. That is interesting. My apologies. I thought it was way more necessary. How did I accidentally do this? Set desktop 2. All right, has something changed? Can you just see my PowerPoint or see more?
Yes, just PowerPoint now.
Just a PowerPoint. Okay, good. Thank you. Thanks for letting me know. Never know what's what maybe student-related information I might have on the other screens. Good. Thanks very much. I do not know how I managed to share 2 screens at the same time. Anyhow, what does the online clicker say? All right, 1 person has begun. About 10 have not begun with assignment 1 just yet. So thanks a lot for letting me know. I'll briefly pull this window down. This is important. First, this was anonymous, so you don't get to feel bad if you haven't started yet. but it also should serve as a reminder, please start as soon as possible. Don't worry, if you have voted incorrectly, I'm not counting this. So this is just an indication to see which direction it's going. Okay. I'm hoping that by Friday or maybe Monday, Wednesday next week, there's more 100 here for yes, I have started. For yes, you have started. Good. All right. So with this brief feedback from your side, let's get started with the actual lecture. So as you all know, the course is called Search-Based Software Engineering. I'm the lecturer and the presenter. Some of the slides are from Justina Petke, colleague of mine from the University College London. I have updated quite a few of the slides, but there's essentially come out of the collaboration here. If you want to learn more about what's happening here in Adelaide in the area of search-based software engineering, have a look here at this website or at my website in general. In general, search-based software engineering is a relatively young field, as I indicated on Monday, and maybe one of the most important works, to some extent, was the tutorial published in 2012. So this is a 20 or 25 page article that tries to summarize, okay, what's the state of the art in search-based software engineering. The field itself is maybe by now roughly 20 years old. There were a few single articles even before that, but we'll cover this in a moment. So this, if you want to have a quick overview over everything that's been going on until 2012, have a look at this article. I've also linked to it as additional reading material. But what is search-based software engineering? It considers two fields. It sits at the intersection, in particular, of search-based optimization. So we're looking at design problems, for example, where you have to make decisions. And we have software engineering, the large field of software engineering, as the other part. And there, where they two touch or overlap, this is where search-based software engineering sits. And typically, with SBSE, or in SBSE, one tries to solve software engineering problems using search-based optimization, or just any form of optimization. Now, when you do optimization, or when you're given a particular task to do by maybe an industry client, you can, in general, you can generate solutions from a very wide spectrum, or through using lots of different technologies. One is that you generate a solution at random. So that's one extreme. The other one is that you really exhaustively enumerate every single solution that is possible, and then you pick the very best one. This exhaustive enumeration is very costly, and it's typically not possible. And somewhere in the middle sits the sweet spot where we say we look at a couple of solutions, we generate some solutions for the client, and then the client can pick whatever he or she prefers most. But we try to be somewhere in the middle, so not just limited to a single solution, but also definitely we cannot resort to just exhaustively enumerating all possible solutions to a problem that the client is giving to us. All these, how do we get to this sweet spot? There are many different technologies that one can use, algorithms, here highlighted in yellow. We can use exhaustive enumeration, we can use grid search, we can use very simple local searches, we can use more advanced simulated modeling or even more advanced genetic algorithms. Sometimes you might have a proper mathematical formulation, in which case we can use linear programming. So there are many different approaches that one can use in order to search the space of solutions. But once we have, this search space it just does not come from anywhere, because if we don't assign any qualities to solutions, we don't have much that can provide us with feedback. So typically, what we have is that in many optimization problems, and this definitely applies here to search-based software engineering as well, that we have a so-called fitness function or a quality function or some way, some component that tells us, okay, this solution is this good, solution B has this quality, solution C has a different quality, and so on. And as a consequence of having all these solutions somehow arranged in a space, it can be a very complex, very high-dimensional space with all these fitnesses, the qualities assigned to them. We can try to navigate this space, to explore this space, and you can try to find really good solutions. Now, why do we actually need search-based software engineering? Let me try to draw some parallels with other problems, probably some that you're very, very familiar with. So some of you might have heard of the 8 queens problem. So in the 8 queens problem, the challenge is as follows. You are given a checkerboard, so with 8 by 8 tiles, so 64 tiles in total, black ones and white ones. And the goal is to place these queens, these are particular chess pieces, in such a way on the board so that they cannot hit each other or kill each other. A queen can hit another one, or has a hitting range to some extent of the following. So it can hit others diagonally. For example, let's consider here this particular queen on the white queen on the black tile can hit maybe along the black lines here, and it can go horizontally and vertically. So in this case, here right now, the queen in the first column, let's make it simpler, the queen in the first column and the queen in the second column, they would not be able to hit each other directly because they sit first in different columns, they sit in different rows, and the diagonals, they are not sharing any line, any diagonal line. So they are fine. In particular here, for this very situation for 8 queens now, has no conflicts, no killing of any queens at all. So you could, assuming that you count the number of queens that you can maybe attack, here the score is in total 0 because no queen can attack another queen. As soon as this works. If we were now, let me go back and forth a little bit. So this is the current situation. If we were now to move, so this queen now up, so to this particular spot here, then we can see that suddenly we can have 2 attacks. We can attack the top, the queen here in the 5th column, and we can attack the queen in the 7th column. So because we have 2 attacks, and for example, we can say an attack is something negative, we want to avoid this, so we can give this a score of -2. So we want to avoid this. Another alternative would be to take the queen in column 5, and move this from its current position, where the overall configuration has a score of 0, move it down here to this particular position, and then suddenly we have 3 attacks for a score of -3. Which is not desired, right? The original goal is to place the queens in such a way that we don't have any attacks. So both examples here, -3 and -2, are definitely not good solutions. Bad solutions. Good. So for 8 queens, it is possible to do this, well, rather easily, by hand even. So this, we can do this by hand. And if I give you, let's say, maybe 5 minutes, maybe 10 minutes, you might be able to do this very easily, or relatively easily, by hand, to place queens on the board so that so that none of the queens attack each other. If you move to a slightly bigger checkerboard, like a sort of an 8 by 8 by the 44 by 44, you might need a little bit more than 10 minutes. I most certainly would need 10 more. More than 10 minutes, and if I give you 10,000 queens on a 10,000 by 10,000 checkerboard, I'm not sure we would be able to do this in our lifetime, to find a solution where there are no attacks. So this is really a really challenging problem. You might say, okay, Marcus, you're never going to encounter any problems like this. Well, effectively, we can. It's large problems, maybe mine scheduling problems, maybe or other problems for large companies. We might actually have to consider 10,000 decision variables, so 10,000 numbers that we have to set. So here it's, for example, 10,000. It depends a little bit on coding. But for example, we can always assume that the first queen sits in the first column, the second queen sits in the second column, the third queen sits in the third column. as soon as we have two queens in the same column, well, we already have an attack, so we can go about it a little bit intelligently. So we have 10,000 variables to optimize here. And you can already see that doing this by hand is probably going to be relatively cumbersome. All right. So let's use the computer, right? In particular, let's look at two different situations, so two different tasks that we have to do when trying to solve this problem. First is, one aspect that greatly helps us is that we need a method that determines whether, given two different placements, so arrangements or configurations, which of them is better. This can, for example, be the fitness function. So I said, do we have a -2, a -3, a -5, maybe, or a 0? So this quality assignment of potentially its numbers to configurations, this can greatly help us to tell two solutions apart and to maybe prefer one good solution over a bad solution. So this assignment, this quality assignment, helps us a great deal, but because then we can use this in order to construct a method that lets us place the queens with trying to minimize the number of attacks. So this is maybe what we would do manually. If we carry this over to search-based software engineering, we also have the situation that, let's start at the bottom. We typically try to create the best solution, but in conventional software engineering, unless you use something like maybe test-driven development or rapid prototyping, essentially you're trying to find the best solution right away. And you're just generating this one single. You're aiming for this perfect solution right away. You're not doing any local search, no fine-tuning. In search-based software engineering now, we do need, because it's search-based, we need this fitness function that will guide us. And so this fitness function will guide us. It will help us to tell two solutions apart. And we can then push it further and essentially use this to guide our search and the fine-tuning. So this is, and this can be automated. And this is a massive advantage of, I would say, of search-based software engineering over the more conventional software engineering, because you can inch towards the goal, you can get closer and closer and closer, potentially. Depending on what your search algorithm lets you do, and depending on the fitness function. So, now you might wonder, okay, what kind of software optimization problems do software engineers actually have? Right? So let's go ahead and ask them. And this is representative of what many different engineers might require at some point. So some engineers might say, hey, we need to satisfy business and technical concerns. Another one might say, we need to reduce the risk during the project while maintaining a completion time. The next one might say, we need to increase, so this is in the systems design, increase cohesion, decrease coupling. Later, a tester might say, we need to find all bugs as quickly as possible. And well, in general, we want to optimize some things. So we optimize our system or something that's being developed, subject to some metrics. A metric is a way of taking, for example, a system as an input, software as an input, and assigning it a quality, assigning it a number. And you can see that essentially with this, depending on who we ask, we've got optimization problems in almost every single aspect of software engineering, whether it's in requirements engineering, in the management, in the design, in the testing, or refactoring is very generic now. In pretty much everything that we do, we have, we can find a way to phrase it as an optimization problem. Almost in many cases. Not everything, but in many cases. And once we have it formulated as an optimization problem, and once we have a fitness function in place that can tell two solutions apart, or can tell us which of two solutions is better, we can automate certain aspects of software engineering. And pretty much whatever you can right now think of, what I can think of, many people have investigated already many different use cases, essentially. Now, excuse me. Now, search for software engineering has this term engineering in the title. There are other engineering disciplines out there, obviously, such as mechanical engineering, electronic engineering, civil engineering, aerospace engineering, whatever. There's many different engineering disciplines. What do you think makes software engineering actually special? What makes it stand out? I hope nobody looked at the next slides already. In case anyone has an idea or wants to just share an idea, just go ahead and either unmute yourself or type it in the chat. What makes software engineering special? What is a big differentiating factor from, for example, aerospace engineering? I'll just give you a couple of seconds. So there will probably, maybe some of you are just shy right now to unmute yourselves and to say something. Can be applied across the boards. Many different disciplines. Software engineering is cheaper, so yeah, okay. Now, so thanks very much for participating and for typing something in the chat. Software engineering is cheaper. Yes and no. So it depends, of course. If you're developing something like Microsoft Windows, it probably costs you a few dollars to put it together. If you develop the next space station, it will also be rather expensive. But let me pick up the cost aspect, because it's also on the slides now. There are obviously some parallels between other engineering disciplines, or let me say physical engineering disciplines, and virtual engineering, like software engineering. In physical engineering, when you want to evaluate something, unless you have a really good simulator, which typically costs lots of money, running a test, so checking what the quality is, for example, of a car, is relatively expensive. But doing a test on a computer is virtually free of charge. Okay, unless of course you go into the dimensions of operating system, in which case a test can also cost a couple of dollars of electricity. But if you can assess the quality of a system, I've done some calculations here. For example, if you can check 100,000 configurations on your, let's say, your average laptop in 1 hour, and you might be able to do this, then the cost is, well, it's essentially for free in terms of electricity costs, because a laptop does not consume very much electricity. Even if you were only able to check maybe one configuration in 1 hour, the check is still 1, 2, 3, 4, 5. It's still, well, maybe a cent or less, potentially less than a cent or less than 2 cents. So it's a very small cost for checking how good is the quality of one solution. And if you can do all these tests for essentially free of charge, you can do all these tests before you deploy the system. So it makes it a lot cheaper. Well, having said this, of course, well, for example, car manufacturers, they rely on simulations for many aspects as well. They rely on human expertise. The same happens in software engineering, of course, but checking the quality or estimating the quality of a solution is just a lot cheaper. Because besides electricity costs, there are no physical costs for, typically, no cost for physical equipment that arise. So there are more parallels between the physical or the traditional engineering and the virtual or software engineering. In both cases, one produces systems. It might be a turbine, it might be a system with lots of dependencies between the individual aspects or components of a system. And for both artifacts that one generates, one has certain goals in mind. For example, and for the turbine, one wishes to increase compression or minimize fuel consumption. In a software system, maybe one wishes to maximize cohesion, minimize coupling, so that afterwards it's easier to maintain. Now, for these traditional engineering artifacts, we might have to rely on very, very elaborate simulators. We are costly and they might not be correct. For software engineering artifacts, we can calculate the fitness to quality by simply running it. This is very often possible. We can run lots of simulations of lots of different hardware or lots of different configurations. This is often easily possible. So it's a big difference here. So prototyping in software engineering is a lot easier than in physical engineering. It has changed a little bit with the rise of 3D printers, but essentially for metal productions, for example, metallic components, it's still not that affordable. So because it's so easy to apply and investigate, researchers have investigated many different areas. And this is just a very brief. I know it's a little bit an old overview, but it still shows how the field developed a little bit over time, and it still is representative of what's happening nowadays in the area of search-based software engineering. This big block here, so for 2001, on the right side, 64%. This is all, the shading doesn't really work, but that's all testing and debugging. It's a massive amount. And this is quite natural, quite straightforward, because, well, if you are a software tester, your client or your team manager says, anyway, okay, I need test cases so that we maximize branch coverage, or we test all branches. So the goal that the team leader gives to you is, hey, you need to maximize branch coverage. And if you want to maximize something, hey, there you go. There's your optimization problem. It's incredibly straightforward. Or you minimize the number of bugs, or minimize the time until we find a bug. A lot of work, because it's just so natural to measure something, the quality of your test suite, a lot of work has focused on testing and debugging. Much more work. But it also covers lots of other areas. There's been some work in the management direction of putting system together or deciding which features need to go into a system by which deadline, managing teams, so putting people, there's no more the management aspect, putting teams with complementary expertise into a team. This has also been tackled. Software verification has not been subject to too many studies, but pretty much everything else that you can think of in the greater software engineering discipline. Somebody tried to formulate it as an optimization problem and has had some form of success with it. And a lot of this is just historically comes out of the search-based software testing. Just because it was so straightforward, and we have got many people who then moved on from software testing to other areas. So we have Francisco Chicano, who is still, for example, very active in software testing. We have Jens Klinke, who does more now in the software slicing domain. We've got Wes Weimer here, one of the first PhD students in the greater area, and he has a company that earns a decent amount of money with search-based software engineering approaches. We've got Mark Harmon here. He has sold the company to Facebook, and he's now probably doing very well at Facebook in London. We also have Bill Langdon was one of the first to improve software, to perform genetic improvement of software. We'll hear about this next week or the following week. We've got people all over the place, and this is, by the way, Justina. She has done a lot, so she's more a traditional optimizer, but then has gotten more into the field of software engineering, and with her working on genetic improvement of software. So it's a very broad, very international setup. We've got Spanish people, many from the UK. So the UK was very successful with attracting money from the research council first, but also nowadays from companies. We've got David White, who's now working for a company, a big software company, has a company with many other people from all over the world. She went to Korea, and Stella is working in Germany, so it's very multidisciplinary. Federica is working in the mobile applications domain. We'll hear about mobile applications in about 3 to 4 weeks. And it all originated here in the, well, largely because it was so easy to get into to some extent from the search-based software testing domain. And well, okay, I'll already moved ahead a little bit here. And certain subsets here of these people, there are of course nowadays many more researchers working in this space. They've branched off into different directions, whether it's structural testing, whether it's combinatorial interaction testing, whether it's test augmentation, regression testing. Like I see, it's essentially testing, mutation testing, state-based testing, model-based testing, black box testing, and so on. So this was a lot on testing, but essentially whatever you can think of in search-based software engineering, somebody has very likely looked at it. Let's briefly check one of people's promotions. Daniel, I will mute you. Sorry. Good. Unless, Daniel, you wanted to say something really important. And of course, please do so. Cool. So an old snapshot of this, unfortunately, the SPSE repository is no longer being maintained. But at this time in 2015, there were easily over 1,000 people had worked on some aspect of SPSE. There were lots and lots of papers from around the world. And we here in Adelaide have been building up a good-sized group with, well, depending on how we count it, maybe 4 to 5 people, also academics, plus at the moment, well, again, depending on how many you count into this, maybe 10 PhD students, plus a whole bunch of coursework projects. So it's a good topic to be working on. Good. Now I've briefly indicated it, but let me make it a bit more explicit. So we need two key ingredients in order to attack something, in order to formulate something as an SPSE problem, and to be able to tackle it. First, when I talk about designs and solutions, we need to have some way of representing the solution in the first place. It might be a graph, it might be a combination of numbers, it might be anything. And we are very flexible with this. So whatever we present, however we can, on a more abstract level, represent a solution without needing to look at the entire source code, that's fine, we can do this. So that's one component. The other one is we need this fitness function, this to guide our search, and this is a real critical aspect. And both these, but the representation and the fitness function, they quite naturally come from, well, two sources. The representation typically comes from the raw data. For example, with the 8 queens, we have numbers, we have integers. With what can we have? With software tests, we can work on source code. We can change the inputs. We can change the integers, for example, or change conditional statements. With where can we get the fitness function from? So there's one aspect we need to settle on the representation, and the fitness function is very often the result of either, let's say, conversations with an industry client, with a team leader, or simply it's the consequence of a metric. You will know in advance, right away, what you're trying to optimize. Maybe it's runtime that you want to minimize memory footprint, maximize again branch coverage or line coverage or whatever. Maybe you will know what you want to optimize, and this gives you your fitness function. You fit both into a general purpose search algorithm, and that's essentially it. This gives you your, and then you're ready to go. You press the button, and then that's it. You can, the search algorithm will then try to find good solutions for their particular problem. In practice, it's of course not entirely quite this easy, but this is essentially a very simple diagram that, well, shows, okay, this is what's needed in order to apply search to your software engineering problem. Many different algorithms are used on the search algorithm side. Far right. This is an old snapshot again. We can see some, well, but very few mathematical approaches like integer programming, not very many at all. We see some hill climbing or local searches. Traditionally, there's a very large amount of so-called evolutionary algorithms. Now, very few of you will have had the chance to attend the evolutionary computation course. It is probably being offered again in the second semester this year. But just to let you know, we will see genetic algorithms in maybe, just a couple of minutes. The advantage with these evolutionary algorithms or genetic algorithms, and just to let you know, genetic algorithms, genetic programming, evolution strategies, estimation of distribution algorithms, Polyson optimization, and so on, they all fall into this greater category of evolutionary algorithms. So this is the super concept. And the appeal of this class of algorithms is that they are fairly robust to design decisions that are not optimal. So your evolutionary algorithm will still achieve something, even though you might not have perfect domain knowledge, you might have made some mistakes with the coding to some extent. It will still often be able to produce some decent solutions. So that's one reason for genetic algorithms just being so popular here in search for software engineering. And we'll see many examples over the next few weeks. But we don't have to go this fancy. We can start with very, very basic approaches. And I've already mentioned the random generation of a solution. It is almost always possible, let's just make it easy and say it's always possible to randomly generate a configuration of a solution. So for example here, let's assume you're giving me the task to generate a solution to the 8 queens problem. And maybe I've done really well so I just threw the queens onto the board. And I've actually done really well because overall here with this particular configuration, I just have 1, 2, 3 attacks. So overall, quite a good solution, I would say. Because there are no attacks here. This one is not attacked by anyone. This one is not attacked by anyone, and so on. So for a randomly generated solution, without thinking, right? So, and you're not doing any local search, you're not doing any fine-tuning, you just randomly generate one single solution. This is probably okay. Now the trouble is that that random search is very unguided and it does not really explore in a controlled way the search space. So assuming that this node does the visualization, let's assume that we can somehow from left to right enumerate all possible solutions to a problem. These randomly generated solutions, they are they are just everywhere, right? And in particular, we are getting some quality feedback, but we're not getting anything that we're exploiting because every time we are just completely forgetting whatever we have seen before, and we just generate the next solution, generate the next solution, completely blind. As a consequence, we might be missing out on this small band here of where the really good solutions sit. That might be reasonably close, but because we never consider the quality of the solutions, actually, when we generate the next one, we don't care, and we just keep generating new randomly keep generating solutions at random. Which is not necessarily a problem because the algorithm for this itself is very easy to implement. Not this much Python code, Java code, whatever you can think of, probably. So, and it's always good to have a baseline approach. Always good to know, okay, especially here with all these optimization approaches, you need to know what happens when you just you need to know how good is your optimization approach. And how do you know how good is your approach if you don't have a point of reference? And this is what random search can give you. In addition, random search can actually form an important part of other algorithms because, you can use it to initialize another algorithm in the sense that you randomly generate a solution and then do your optimization job. You generate another random solution and optimize from there and so on. Random search is one approach, very simple, and don't worry, we'll take a very brief break very soon. So random search is one approach. Let's think of a different approach. So I said a few times here, we're not considering what we've seen before when generating new solutions. Let's consider hill climbing as an alternative, or sometimes called local search as well. Let's imagine the following. Unfortunately, because we are not in a room, I cannot walk around. Normally in these lectures, I would walk around in the room to show, okay, we are now in a local minimum at a low position. I'm looking around, I'm doing steps to the left and right, and sometimes I hit maybe a stair, and then I can walk up the stair in order to get better and better, or higher and higher in this lecture theater. Right now, you just have to imagine me walking around in the lecture theater. So the way hill climbing works is as follows. It's super simple. We generate one solution. Just imagine me being standing at the very front, and then we look around in the neighborhood. The neighborhood can, for example, be defined in a room by doing one step to the left, one step to the right, one step forward or backward. So we look around, and if I get to a better solution, a higher spot in the room, if I make a step, let's say to the front or forward, then I would accept this new solution. And then I would, yes. So if the fitness is better, I accept it, and then I go back into my loop. I look into the neighborhood. If it's better, I take it. If it's better, I take it. If it's better, I take it, and so on. And this way, within the room, I might be able to climb up and up and up inside of the room. And the same concept works also for website level for optimization approaches. I have a particular configuration, for example, with the queens. I have them sitting at different positions, and I can take one queen, move it by a little bit up or down, and then check, okay, is this solution better? If the solution is better, hey, I found apparently a better solution, all right? And I can take it as a starting point. I can accept it and take it as a starting point for the next search. So I can take this slightly better solution, make one small change to it, check, is it better? No, then discard it. Make another change to it. Is it better? No, discard it. Make another change to it. Is it better? Hey, yes, it's better. Okay, then I take it as a starting point again. So very, very simple. And as Lantian says in the chat, yes, it is a little bit more complex than random picking, but you can see here it's 3, 4 lines, 5 lines, so if you want to, 5 lines of pseudocode. So if you implement it, it's about 5 lines of Python code. It's really not very difficult. Well, okay, some implementation details are, of course, hidden in things like, okay, what's the neighborhood, what's the fitness, but overall, it's a very, very simple loop. Generate something, is it better, accept it, is it better, accept it. And there are actually, among this hill climbing, there are many different variants. There's the variant where, well, you check the neighborhood, you just generate a single point in the neighborhood, and if it's better, you accept it. Then there is the version which is listed here. You go through, you can go through the entire neighborhood. So enumerate all possible neighbors, and then you select the best solution from this entire neighborhood. And then there are other versions out there as well. But for now, yeah, let's consider a simple hill climbing, simple local search. You write one solution, you generate one new solution. If it's better, you accept it. Now, there's one important aspect here that I should put into the slides at some point in time. This is accepting solutions if it's better, or strictly better. Oh, yeah. If it's strictly better, the problem with this is that you might end up on a plateau, so on a flat area like a table, and you do steps to the left, you do steps to the right, forward and backward, and all the fitnesses are always the same. This is not necessarily fantastic if you have such a strict requirement that the fitness has to be strictly better. Right? This is greater than, it is not greater than or equal. This is a big difference, at least in discrete spaces. The trouble here is, well, you can simply not explore it. You might get stuck very quickly. If you accept solutions if they are not worse, or if they are, in this case, for example, greater than or equal to the one that you have at the moment, this actually allows you to walk around on the plateau, on the flat area. And when you can walk around, well, even though it's endlessly, right? But if you can walk around on this plateau, you can potentially find a point from where on you can find better solutions. But if you have this strict requirement of just strict fitness improvement, you get stuck right away. So leaving some room there for a random search again across over this plateau is very important. Now, in the 8 queens case now, hill climbing can look, for example, as follows. So let's assume we have this current situation with a score of -2, so we have 2 attacks. And now a neighbor can, for example, look as follows, where we move the screen just 1 field up, from here to here. And now, well, because of the way the example was created, previously we had a score of -2. Now we move it up by 1. And now we have a score of -1, because we say we want to minimize the number of attacks. Hey, this solution is no better. Very easy. Now, what can we do next? If we move it 1 further up, we are probably stuck. We have at least a hit of 1. We have a score of -2. Over there, we have at least -1. Here we have -1. We can go down again, and then we have -2 again. So depending on what kind of algorithm we use, we can actually be stuck here. And we cannot get to a score of 0. Not by changing this queen. We might have to change another queen in order to get from the -1 to a 0 eventually. But as the example here, I'm just jumping back and forth, going from -2 to -1 would be seen as a good step of this fine-tuning, and we can continue with this. Good. A question for you. Will this, and I might actually have given this away a little bit already, hill climbing is a nice approach. Will this always give you the optimal solution? Can it actually find the optimal solution to your problem at all times? Lantian says it's an NP problem. The problem is defined differently. So this is now talking about the algorithm. Right, so I'm getting lots of no's. Correct. So hill climbing is not guaranteed to find you the optimal solution. Here's a bonus question. How about random search? Can random search always find the optimal solution? Let's say who else put something up. Stop in the edge. No, we're talking about random search. So purely just random generation. You generate a new solution, generate a new solution, generate a new solution, generate a new solution. Can this always find the optimal solution? Okay. So technically it can, but you might have to wait infinite time. It depends a bit on. It's not necessarily infinite. It depends a bit on whether you consider what kind of problems you're considering. If you just have 2 solutions, it depends a bit on how big your solution space is. But essentially, if you're generating solution, you will not need infinite time, but potentially you need a very, very, very long time to hit the optimal solution. So it's impractical not in this case. So to illustrate that we cannot always, for those of you who don't believe it, correct. Thanks, Sharon. Yes, you're right. So for those of you who haven't quite seen it, that hill climbing can get stuck sometimes. Let's assume again from left to right we have our space of possible solutions here. This is the area where we have really great solutions, and if we use our hill climbing approach where we climb up the hill, if we start at this point, we can get stuck here, because from here on we go left and right, small steps, and we cannot make it far enough. But if we get lucky and maybe start somewhere else here, this ridge here, we might be able to get closer and closer and higher. If we find the right changes that we need to make and arrive at the optimal solution. And that's actually a very big advantage here of hill climbing. It can get us at least into local optima. Local optima are nice because you can investigate them. You can learn something about the problem. And also you know that, well, you know that once you're in the local optimum, you can, if you make small changes, you're getting worse. So you have a tiny little bit of a performance guarantee. And essentially, once you're stuck, you have no idea, because you do not have complete problem knowledge of the problem. When you're stuck here, you do not know whether there's a solution like this one, that's another 20% better, or there might be this one that's 100% better in terms of quality. You do not know this for many, many problems out there. There are artificial problems where you know, or sometimes by construction, you know that values like, for example, 0 are achievable, or 100, or any kind of magic numbers are achievable, but you might not know what is the solution, what does it look like, and then this is where you need these searches. Now, the previous situation has already outlined one challenge. So we can get into a local optimum, end up here, but then we are stuck. Wouldn't it be nice if we can actually get out of this local optimum by going away a little bit and then going up again? And this is where simulated annealing can help us. What I'll do now is the following. So simulated annealing can be seen as an extension of reclining. What I'll now do is the following. I will briefly break you all break you up into these breakout groups, and I'll give you about 2 to 3 minutes to read this pseudocode. It's just a small extension of reclining, and there are 2 questions for you. First, which lines in here are responsible for, which lines here let us actually accept our solutions? And the second one is this code actually for minimization or for maximization problems? Because this will affect a little bit how to interpret this. Here's the breakout group. So we'll get you all back in, let's say, 3 minutes or 2 minutes, and then I'll press the button, and then you have 1 minute to come back, or you will be pulled back automatically. We have 18 students here. Let's say 4 groups, 5 groups, maybe 4 groups. Right now, I'm over into this, and I'll say a few things now in the chat. Yes. Let's breakout was not started. What is happening? Move to. And then can anyone please confirm that he or she can still hear me? Something has. Yes, okay, you can still hear me. Okay, I have the interesting, unusual technical problem because when I used it today at the DevNet talk, it worked. That I cannot send you into the breakout rooms. I have the breakout rooms now. Open rooms. No.
分配咗房之後，我睇不到問題。分配咗房間之後，我睇不到問題。I can't see the problem after allocating the bay.
Right, I see that some of you are already back. We still need to wait 16 seconds for everyone else to come back here into the main room. All right, many of you are coming back. It's fantastic. Thank you. Let's give you just another few seconds. Good, we have everybody back again. All right. Now this was potentially a lot of pseudocode. On the other hand, it's also very easy to read pseudocode, I'd like to think. So coming to the questions here, which lines do you think let us accept worse solutions? And which group feels confident and says, yeah, we found out which solution, which lines let us accept something? Anyone?
I think the iterations. I think the unit iteration equals number solution force us to accept the worst solution, because until this step, if the iteration generate is full, we should quit the program.
Okay, I'm realizing I should be using some line numbers here. Sorry, which you're referring to? It was this the generate random numbers, or you said which lines? Iterations, this line? I'll be adding line numbers soon, so just I can't do this on the fly. Let me start here with with this particular loop here. So we look into the neighborhood, we change, we generate a new solution S prime. We consider the difference in the performance between S and S prime. And if this delta, this different performance difference is less than 0, then apparently we'll always accept it. If it's not, less than 0, so if it's greater than 0, then apparently we do something magical. Well, it's not magical, it's not but then we do something. So it's actually this part, and maybe some of you have managed to find this. It's this, sorry, not iterations, it's this else here, that's essentially the extension over hill climbing. Because in hill climbing, we always accept a solution if the new one is better, and this is exactly what we have here. If the solution is better, so if the performance difference is less than 0, then we accept it. If it's not, well, then we do something. But what do we do? Well, 2 steps. The first step is that we generate a random number. And then we put it here into this expression. So if the random number is less than or equal e to the power of minus delta, so it's something performance dependent, over t. But what is t? T seems to be an initial temperature. Why is it temperature? Something that I had not told you a little bit on purpose is that simulated annealing comes, well, at least has its name, the inspiration from metallurgy, so metal processing, the science of metal handling. What you can do with certain metals is you heat it up, you let it cool down slowly, you heat it up, you cool it down again slowly, and through this cooling down, you can the metal relaxes, or some of the stresses within the metal relaxes, the crystalline structures align better, and as a consequence, your product gets better. And we can use this concept here, but this is a very loose translation of heating up a solution and cooling it down. In this case, it's just starting with a really hot solution. starting with a system that is very hot, we can use a somewhat similar approach here in order to accept worse solutions. I won't do this now for you, but I'll maybe you can try this out at home briefly. See what happens as the temperature decreases over time. So let's say initially your temperature might be 1000, so it doesn't have particular units here, so just see it as a scalar. Let's say 1000 units. And then you gradually decrease it, and towards the end your temperature is maybe a 0 or a 1. So apparently this has some effect on here on these expressions, so it's e to the power of minus delta over 1000 or minus delta over 1. And depending then on how big or small this performance difference is, this expression here will actually be either rather small or large. What we wish to have is now, let me go back one slide. The idea of the temperature is the following, and in particular, the temperature should decrease somehow over time. The motivation is the following. Initially, when we run our simulated annealing algorithm, we might want to have a very high chance of jumping out of the local optimum. So we are still, keep this in mind. So I go forward again. We're always accepting better solutions, right? We're always accepting better solutions. This never changes. It has nothing to do with temperature. We always accept better solutions. But we also want to accept worse solutions. But maybe if we accept worse solutions at the very, very end, when we actually want to try some fine-tuning, this is too late. So we don't want to spend our time exploring the space again. But maybe initially we want to explore the space. So we want to jump around very big if we are stuck. And as the system cools down, as our algorithm cools down, the temperature decreases, and we are less and less likely to accept it. So I invite you to, at home, to look into this, to both check, double check those questions number 1 and 2. Number 2, I will not start here right now. Plug in some numbers, see what happens when you have a performance difference of, for example, 1000, and initially a temperature of 1000, versus a performance difference of a difference of 1000 later and a temperature of 1. So the fraction here will obviously looks different, so it's minus 1000 over 1. And what's e to the power of minus 1000 over 1? And this is just a check to do something randomly, because we do not always want to check or to accept worse solutions. We just want to have a certain probability. Because otherwise, if we accept a worse solution late into the process, we might be jumping far away, and we are losing potentially this really good spot here, maybe this mountain that or this particular part of this mountainous area that we've discovered towards the end of the optimization. So initially, we want to have a high chance of accepting something worse, or towards the end, not so much anymore. And this is what this temperature can give us. Good. So again, compared to hill climbing, compared to random search, this looks a little bit more complex, but it actually is not. It needs, okay, in this case, about 15 lines of pseudocode, but you can reuse all other components. You have the neighborhoods that you needed on some generation of a new solution that you needed definitely for the hill climbing. You have the initialization here at the beginning. You have the fitness function. These are all components that once you've made it to simulated annealing, you already have in place. And let me just briefly show you. I think I should be able to jump back. There it comes. 1 second, please. Where we had the overview with the different papers. So simulated annealing is still reasonably popular because it's a small extension over. We don't even have local search, but hill climbing here. So hill climbing, random search is not here on this list. Hill climbing is very easy to implement. Simulated annealing is a little bit more. Is a little bit more complex. It needs this 1 or 2 additional components: the temperature that decreases over time in some way, and it has this probabilistic acceptance of a worse solution. It is also a bit more popular than hill climbing, even though it requires these additional components, because it can potentially give you better solutions, right? This is this has been the motivation in the first place. because we want to have some probability, some chance at least, some possibility of making it out of a local optimum and climbing up into a different local optimum, and then maybe eventually finding even here the global optimum in this particular case. Good, so this is simulated annealing. Thanks to those of you who have discussed. Please do run the numbers, just do some brief checks with big numbers and small numbers like 1001 for both temperature and performance difference, and see what happens. You're most welcome to just post your observations then on the discussions forum, and we can discuss there a little bit whether your calculations have been right, and also the interpretation, of course. Quick disclaimer: this is all voluntary. You will not get marked for this, but you can get feedback. Right. Now, this is the third approach. There's one final one that I'll briefly talk about together with the case study. But actually, given that I've been talking now for an hour, let's do the following. I'll do a 2-minute break now, and then we continue with genetic algorithms. 2-minute break now. We continue at 2:21. 2:21. Short break to stretch yourself a bit.
May I have some question?
Sure, go ahead, ask.
I think the SBSE is so special because it combines the searching algorithm with the software engineering. Mm-hmm. But I wonder which part could apply those things. For example, if I'm a coder, I'm not a project manager, can I use SBSE?
Yes, you can definitely do this. It depends again greatly on what your challenge is. We will see a few examples now and over the next weeks, even on the code side. So you can have, for example, configuration optimization. You want to maximize the speed of your implementation, minimize memory footprint. So these are things where some optimization, where you are not entirely sure, should this buffer size be 1,000 or 100? For example, I'm making a very simple example. This can help. Do you have a bug? How can you fix the bug? Maybe you can have a system, and this is, for example, what Wesley is earning some of his money with, is with bug fixing, automated bug fixing.
Okay.
So it's definitely possible to do this also at the very, the code level. And we have, maybe in 3 weeks, you will hear from either me or from someone else here from our team. We are currently working on side channel leakage minimization. So we work with assembly code, machine code. Cool. So that's all possible.
Yeah. What about refactoring and release planning? Is that still okay?
Sure. Release planning is not necessarily something that I've done. I know other people have looked into this to decide, for example, what software product lines, what features should go into what systems and by when, what are the chances of a feature not being implemented in time. So you can do a lot in this direction. Yes.
So, yeah, in this case, I think almost everything in this SE can combine with SBS. Yes. Okay, thank you.
I can't immediately think of something. Well, when you involve humans, this is maybe like graphical user interface testing or so. This might be a little tricky. So replacing this, unless you have somebody who just randomly presses buttons, but you can always simulate this. So certain aspects you might not be able to automate, but in some cases it might be possible. So then the system can help you. Sure. Okay, maybe let's extend the pause for another short break for another 30 seconds, because I can drink something. Good. Very quickly, it has turned 2:22. So, super brief recap. I really want to highlight that it's the algorithms that we will be using here are simple. simple. I've got random search, we have got hill climbing. So far, we have simulated annealing that has a chance of getting us out of the local optimum. And now, as essentially the fourth last class of algorithms, let's have a look at genetic algorithms or evolutionary algorithms. If you want to learn more about this, I can point you at more information or go and attend the evolutionary computation course if that's possible, and it's not always offered. But yeah, so there are many different concepts out there. This is not the focus of this course. In this course, we will focus on examples and on formulating situations as optimization problems. And then these 4 concepts that we have essentially seen today, this one we'll have seen in about 5 minutes, they will give you a very good starting point. Random search, local search, simulated annealing, and genetic algorithms. They will get you quite far. Okay, what is it? Sorry, now let's start here with the picture. One of the outstanding features of a genetic algorithm over, for example, simulated annealing is that instead of searching with just a single solution at all times, a genetic algorithm can search with a population. It's referred to as a population, so a set of solutions. Here we have 1, 2, 3, 4, 5, 6, 7 different solutions, and they all sit somewhere in the space. And now the motivation here is a little bit because we want to mimic evolution as it happens in the real world, that we can, sometimes combine information, like you're the result of recombining genetic material of your parents. We can maybe also recombine information here at the solution, at the configuration level, and then find better solutions here to a software problem. I know this is a bit contrived example here, but if we were to be able to construct, to have this solution here and the one just to the right of the really good solutions produce a new solution, a new configuration, then this might have a very superior performance. Of course, by no means guaranteed to find better solutions. So, for example, if we combine this solution here and this one, the solution might actually end up somewhere down here in this valley and might perform worse. So there's no performance guarantee, but we are not so much after performance guarantees here, we're not after performance guarantees, but we are after the possibilities. So having a small chance of finding a good solution. This is enough. It shouldn't be super small. It should not be 0.00001%, because if it's that small, we will never encounter it. Good. What does a genetic algorithm look like? There are lots of different flavors of it out there. And what I'm showing you here, this pseudocode is just one variant. You can change quite a few components and it will still largely work. I will not go into the details here, but this is enough for you to get you going with your homework, definitely. And you will be able to understand many papers just based on this skeleton, based on this framework. So in a genetic algorithm, just like with all the other approaches, initially we have to generate our solutions. So that the first one, for example, or several, with this at random, or we can what's also what one can refer to as seeding. So we can start with a known good solution. This is nothing specific to genetic algorithms. We can do this for local search and for hill climbing, of course, as well. And we might have a good solution already because maybe we know something from the literature. Maybe the customer has given us something and says, okay, take the system and make it better. Or, well, in this case, the requirement is actually that you take the system and make it better. So you can take it as a starting point. Or you can compute what the customer has said or produced and try to generate something completely from scratch. All right, so that's step one, generate. That one is set the initial population. So the set P of, on the previous slide, 7 solutions. Right, need 7 fingers here. And then we have a loop, much like with hill climbing and simulated annealing. What we do here is the following. Well, first, and it's one artifact because we didn't check the quality of our population. But first, we evaluate the quality of the solutions in our population. Then we select some parents, prospective parents from the population. We have some mechanism for it. We'll see an example. So these parents then mate, they produce an offspring, they produce children, software. Then we somehow we construct a new population based on the parents and the offspring. We might change some of the population members a little bit more, and that's it. The old population gets overwritten, and then we continue. We calculate the fitness of each of the solutions. We select parents, the parents produce offspring, some of them survive, and then we continue. Produce offspring, some survive, produce offspring, some survive, and so on. And this goes on and on and on until we've run out of time, run out of money, we've reached the quality of a particular solution, and so on. So lots of different ways. In case this was a little bit abstract for you, let's go through a brief case study, and Lantian, remind me of your question at the very end, please, of this lecture. So for genetic algorithms, let's have a look at the case study. Let's say your company has 1 million test cases for some software, which is good, but running all 1 million test cases takes a while. Test. The goal now might be to sort these 1 million tests so that you detect bugs as quickly as possible. So given our, for example, a test suite, so your 1 million tests, and you want to arrange them sequentially, one by one. So you're looking for a set of permutation, or one permutation of these 1 million test cases that achieves something. And in particular, you are looking, for example, for the very best permutation that finds the bugs as quickly as possible. So what this just says is, you try to find the permutation that essentially for all other permutations that look differently, your permutation is the best. What I have not told you is how to, what to measure. And for example, you might want to measure the fault detection rate. So how quickly do you find bugs? So this might be the goal, because you can definitely always run 1 million test cases, but it might it simply takes the runtime of 1 million tests, running 1 million tests. However, if there are duplicates, or if you haven't implemented certain features, why even bother to run all of these? So why not try to sort them in such a way that you cover much of the code very quickly, and maybe even find historic bugs as quickly as possible. The use in regression testing now is, because you have this regression testing is the situation where you do regression testing to see whether there have been regressions. So in regression is when your code becomes worse due to a change. Because you have a fault or a history of bugs recorded, and you might maybe accidentally undo something, you commit something to the repository, and you accidentally undo a bug fix, or you introduce a copy of an old bug, hey, then if you're able to detect this bug as quickly as possible, then you save time and electricity. So that's the motivation. Well, you might remember from about 45 minutes ago that we need these two key ingredients in order to approach something using optimization, to formulate something as an SPLC problem. First one is the representation. Second one is we need a fitness function. Let's do one at a time. Representation first. And this is very easy, I think. You might remember from a while ago. Raw data results in representation very often. In our case, we are not looking at 1 million test cases here, but just 6. Right, we keep it a little bit simple here on the slides, just 6. And a permutation can simply be the 6 numbers, so 1, 3, 6, 2, 5, 4. So these are the tests or indices or identifiers, whatever. We're just looking for a permutation of these 6. So that's easy. Once we have one of these permutations, we can also easily define neighboring solutions. So these are solutions that are largely the same, but they differ maybe in some small part. One way you can, there are many other ways, but one way you can define a neighboring solution here, for example, based on 136254, is by leaving many numbers unchanged, and for example, swapping two neighboring numbers. So instead of having 6, 2, you have 2, 6. The permutation is not different, but now you're, well, in case 2 detects a bug that was not covered by the other ones before, maybe this sequence now is a lot better, going 1, 3, 2, 6, 5, 4. I should just imagine that 6 was a copy of 3, largely. So then executing 6 is just not beneficial. But you wouldn't necessarily know this because 6 and 3 are, well, it's source code. You would have to understand really what each test case does. Well, or maybe it's simply run. You would prefer to do, let's say, test case 6 runs for 1 hour, but other tests you can run very, very quickly, and this way you ramp up your, the rate at which you detect bugs. You can increase it much quickly and have a higher detection rate. I've used a lot of hands and was very vague with my definition here. An alternative to this is, well, because also, once you implement it, you have to implement the average percentage of false metric. I think we'll have a plot of this later on. Essentially, what this metric tells you is that if it's higher, the value, so it tries to compress essentially a guess. It calculates for a permutation how quickly you find bugs, and the higher this one number is for the permutation in the end, the quicker you find faults. The alternative would be simply the other way around, it would be a poor example now, where you execute lots and lots of, let's say, copies over and over again of the same test. You're not making any progress, and you're just wasting time by executing comparable test cases over and over. So ideally, very quickly, you cover as many different faults as possible. There are lots of variants out there. This is an old paper, but it was one of the first ones to do it here. The paper from about, nowadays, 20 years ago. But it is a very accessible one. So if you have a few minutes, have a look at it later. General, I see your question. I'll respond to it afterwards briefly. Good. All right, so we have our two components now in place. We have the average percentage of faults detected from the previous slide. We have the permutation as our representation for our test suite ordering. And now we can put this into our search algorithm, and because this is the case study for genetic algorithm, let's simply use a genetic algorithm. So the search algorithm is a genetic algorithm. This is again the pseudocode. Unchanged to before. I'm not just filling a new line. This is now how we will try to solve this problem using a genetic algorithm. Let's go through this step by step. First step is, well, we randomly generate some permutations, and let's just assume that we have a way to generate permutations. There are several different ways to do this. These are now 4 solutions, population of size 4. In practice, people tend to use larger populations, but here on the slides, 4 solutions is easy to visualize. 4 different permutations. So this one is 1, 3, 6, and so on. This one is 2, 5, 1, and so on. 1, 3, 2, and so on. 6, 4, 3, and so on. So these 4 orderings of the potentially 1 million, but here it's just 6 test cases. These are simply our orderings. And let's assume that we have a way of running the tests and to determine what is our average percentage of faults detected. If you have any questions during is this a really important question? Or maybe it was just an accidental unmute? Okay, no problem. We'll take a short break very soon again. So let's assume we have a way of executing these 4 permutations, and our metric then says the first one has a quality of 68, the second one of 55, 72, and 78. So 55 is the worst, solution at the moment, 78 is the highest one. Now, as a human, we might or might not be able to determine something. Maybe we could see some patterns here. We could maybe determine what makes up a good solution or a not so good solution. But once we're looking at the 1 million test cases, it's just out of question. A black box approach, a search-based software engineering approach is the easiest thing to handle, or for this to handle. Good. So that's the second step. We have evaluated the quality of our individuals, of the individual solutions in the population. And now we select our parents. We can select parents in many different ways. For example, we can just randomly take 2 parents. So in this case, I go back and forth. I'll just refer to the solutions via the quality. So there's a 68% and 55%, and 72 and 78. So we can randomly or maybe sequentially pick 68 and 55 as parents. But we can also say, maybe we actually just take the better one of 2. So we pick a pair randomly from the population, but just take the best one of this pair. You can consider 78 and 72, and again, just pick the best one. This way we have a bit of a selection pressure towards better and better solutions. Because keep this in mind, if we keep doing mutations and crossovers, if we keep searching a lot using bad solutions, we will potentially waste a lot of time. So we have to focus a little bit on the good solutions. And in this case, what we've done, we run a true tournament. So a tournament, a selection from two solutions. We let them battle against each other. And the better solution in this case here was the 78, so the 78 gets to be a parent. So these two were selected by the 2 tournament. This one was from the 68 against the 55, and then this one is the 78 against the 72. And now they get to create a new offspring, a new solution. How do we do this in genetic algorithms? Well, we can do this using crossover. And there are many, many different crossover operators. Crossover is just a fancy way of saying it's a recombination, creating a new solution by recombining material from the parents. What can we do? Well, we have to be aware of some potential traps here. This is the solution with the quality 68, and this is, was it 68? I have to go back. Yeah, 68 and 78. So this is the solution with quality 68, this is the solution with quality 78. If we were to just cut them off in the middle and then swap parts, we might end up with with invalid solutions. So, for example, if I were to copy over this to a child, I can of course do this. So going 1, 3, 6 for this one. But if I then copy over either the first part or the second part from the second parent, so this is parent 1, parent 2. If I copy over either the first part or the second part simply from this cutting point, I end up either with the 6 again here or with the 1 again here. So I have either 2 6s or 2 3s or 2 1s in the same solution. And this is not a valid permutation. Luckily, there are simple ways of dealing with this, and one is the following. For example, we can still copy over parts, and say we copy from parent 1 to the child 1, so 1, 3, 6, 1, 3, 6. We simply copy this blue part over. But then, well, how do we take some information from the second parent? It's very straightforward. We can go simply from left to right and copy over the missing numbers. What are the missing numbers in sequence, in the order? Well, if we go from left to right, well, the 6 is already here, right? So we wouldn't be copying it over. But the 4 is not there, so we copy it over. The 3 is already there, so we're not considering it as the 5 is not copied over, so it's not there yet, so we copy it over, and the 2 is missing. Well, the 1 is again there, but the 2 is missing, so we copy over the 2. Similarly here, I guess we'll be able to fill this out. So we have 6, 4, 3 copied over from the second parent to the second child. What information in which order? Next over here. Well, the 1 is not there yet. In order 3 is there already, so we skip it. 6 is already there. 2 is missing, so we copy it over. 5 is missing, so we copy it over. 4 is not there. And now we've created two solutions, two new ones. And they are valid permutations. Fantastic. So what's next? Well, we can sometimes, well, change the population just a little bit more as well, because the problem can be if, well, essentially the parents get to recombine and produce offspring and recombine and produce offspring. At some point, we end up with lots of, well, solutions that look very much the same. We have no genetic diversity, and this is not necessarily good. It's bad in the real world, and it's bad here in optimization as well, because we can be stuck. So we need something this comes in with and disrupts it. And in the real world, this is called a mutation, and we call this also mutation in genetic algorithms. What a mutation can do is, for example, it takes a solution and it ever so slightly changes it. So previously it was a 2,5 here, for example, and it changes it to a 5,2. Here goes from a 4,3 to a 3,2, 1,3, 3,1, and so on. And this now forms the next parameter population. Then we start again. We evaluate it, how good are the solutions. We let them, when we do the parent selection using a true tournament, for example, they create offspring, and so on. We go round and round and round until, well, again, maybe the time is up, or some computation budget limit is reached, and so on. Very simple, relatively simple to implement. In code, you notice it's a little bit more. In Python, I believe you can code this up, but maybe if it's looking just at this, it's really not much more. It's just the 10 lines of code here, 12 lines of code, plus some helper functions, but it's really, really simple. And all the approaches, like the mutation operators, crossover operators, they're not very problem specific in this case, where we just copied parts over where they were missing. They're all very generic. They're not considering anything at all that is specific to test case prioritization. They're just working on permutations. The only thing that makes it proper test case specific is the fitness function. To this amount, it's overall very generic. It's going to be very generic and very simple to implement. Good. Yes. Just to very, very briefly let you know this, genetic algorithms are one paradigm. There are also other schemes out there, like, for example, genetic programming. In genetic programming, we would not so much be working on numbers, on sequences or permutations, but in genetic programming, you can actually evolve graphs, for example, or other structures that can represent code blocks, and you can, in this case, you might be able to see this, that some part was crossed over, so this solution, we cancel part, and we remove part of the graph, and we copy part of another graph over. Now we have the recombination here of two graphs. On the left side, we can see, I think, the mutation of a tree. So we have this tree where part gets deleted, and then a new tree gets grown up, gets grown. So some part of the solution still is maintained, but some other part is generated. In general, here in the large area of Sofware software engineering, there's a lot that one can look at, one can consider, many different flavors. We will keep it relatively basic here in this semester, because that's not the purpose. We're not so much concerned with lots of different, very advanced technologies, but with formulating something as an optimization problem. And again, I really want, so I'm sorry that I'm repeating this over and over again. Random search is a very good starting point. Hill climbing is the natural next step, then simulated annealing, and then genetic programming. All genetic algorithms, sorry. All very easy to implement. Very easy. Good. I've seen two questions here. One is from, I'll start with Cheng Hao. Cheng Hao asks, a genetic algorithm won't guarantee the best result. That is absolutely correct. We have no performance guarantee for genetic algorithms. This is good and bad at the same time. Actually, I'm not sure what is good about it. The bad thing is because we don't have a performance guarantee. The way we normally show that something works using genetic algorithms is through rigorous experiments. showing that it's robust, that it works under many different conditions when we have different scenarios. This is how we show that it's a good approach when we write something. Martin asked briefly about pseudocode, and maybe this was just the way it was inconsistently represented here. Everything is very simple to implement. The fact that in simulated annealing we have some numbers in there and a brief equation, all that the equation in simulated annealing does is it gives us a probability, and this probability depends on, well, it's not just completely random, otherwise it would be in Java just math not random, but it's a probability that depends on the distance between two solutions and so the performance difference or quality difference and the temperature of the system. So it's not necessarily harder to implement, but of course, random search is the easiest to implement. The local search is a little bit more complex. Simulated annealing is a little bit more complex. Genetic algorithms are again more complex because you need, well, the mutation operator is essentially your neighborhood, your small change that you also need for local search. You need the recombination. You need the way of constructing a new population, which you can do in many different ways as well. So genetic algorithms are probably the most complex ones. But again, it's very generic, so it's not very problem specific typically. Once you have a representation and once you have a fitness function, this gets you very, very far. All right, let me grab a sip of water. Okay, there's one more thing that I want to briefly talk about in the remaining 10 minutes, and that's the following. This is multi-objective optimization. Again, a brief primer in the evolutionary optimization or evolutionary computation course, we would spend 2 hours at least on this and several home assignments. In this case, time is a little bit limited here, so here in SPSE. So, very brief outline of what multi-objective optimization is. You might remember this slide from about an hour ago. Software engineers have all different kinds of challenges that they're facing. And as you can maybe imagine, some of them are in conflict with each other. So maybe somebody wants to reduce the risk while trying to get as much done by a deadline as possible. Somebody else might have all these different ways of assessing how good the system is. Let's think of the following. Computation speed versus energy consumption. Maybe somebody wants to maximize, optimize the speed, so minimize time, but also use the minimum amount of energy. On the other hand, you can minimize time probably by using just a very, very fast approach, but a very fast approach with a particular algorithm might also require maybe multiple cores, so maybe your energy consumption actually goes up. So you have something very fast, but something that doesn't run that also requires a lot of energy for this. So there are often trade-offs that you're looking for. So far, all the algorithms are random search, hill climbing, I'll just go through once more, simulated annealing, genetic algorithms, they typically only consider a single objective at a time. But there's also the large field of multi-objective optimization, and this differs in, so this is not, what we'll cover over the next 5 or so slides, these are not different algorithms, this is a different way of looking at a particular problem. And this is important because we now cannot simply look at a single objective, single fitness value anymore. We are not just going for speed, but we have maybe speed versus price versus reliability. And because it's a little bit easier to think about this, let's think of cars. So if I were to buy a new car, maybe I have to trade off certain things. Well, one is maybe, okay, in Adelaide I can't drive particularly fast, but let's assume I want to trade off, I want to have the fastest car for the lowest price and with highest reliability. how do I squeeze everything into one fitness function? I cannot add kilometers per hour and dollars and whatever reliability is. It's like I like to do this, say a phone plus 1 cup, or what is 2 phones and half a cup? What is better? I cannot add these 2 things up together. It doesn't make sense. The units don't line up. And this is something that we have very often in problems, in design problems. For example, in engineering problems, you have the lightness in kilograms of a piece of kit, and we have the strength or durability. So now suddenly we have two problems. First, we have to find a good set of solutions, and then in addition, we eventually have to pick one of these sets. Let's look at clouds, for example. So again, in many optimization problems or many real-world problems, we might just have a single objective like comfort. In some situations, I might have 2 objectives like speed. So I have not particularly fast and not very comfortable car here in the bottom left corner. And as I maximize speed, I might end up here at a racing car. If I maximize comfort, I might end up here as an RV. And in between are trade-offs. So somewhere in between, or somewhere maybe probably down here is my actual car. Not very fast, not very speedy, but it represents a speed of trade-off. So it's technically this car here is so the RV here is it's a lot more comfortable. So it beats the racing car in comfort, but it does not beat the racing car in speed. So what do you do? These two are now. How can you tell them apart? And actually, you can't really tell them apart. They are what I'm already jumping ahead a little bit. They are what we call incomparable. Whatever sits here along this trade-off line is actually incomparable. But you can compare them, but you cannot really say one is better than the other solution. So the first thing is there's no single optimal function value. This makes it difficult for us, for the algorithms, to say, okay, what do I actually now keep? What do I consider for my local search? And in the end, well, ideally, we represent some trade-off set to a decision maker. At a more abstract level, what we typically do in multi-objective optimization is the following. We start with solutions that are not necessarily fantastic. So let's say here in the bottom left corner, we're maximizing objective 1, maximizing objective 2, and you want to evolve these solutions over time, so from generation to generation to generation, so that we nicely cover this trade-off set, these Pareto optimal solutions. These solutions are called Pareto optimal because you cannot improve, for example, this solution here in both objectives at the same time. It's right there. As soon as you go to the left, you get worse in one and better in the other. As soon as you go to the right, you get worse in one and better in the other. Compared to this situation, for example, this solution, these three, they are not Pareto optimal because both you can optimize and can improve in both objectives. Not here once you add the Pareto's set element. Now I already said that once we have them there or on this front, we can't really compare them anymore. So there is no different figure. But we can still say something about some parts of the space, of this trade-off space. In particular, here we have solution X along this Pareto front again, and I should probably update this a bit. And we say that all the solutions that sit behind it, so they are worse in objective 1, sorry, F1 here, and worse in objective 2, they're all dominated by X. So X is dominating this entire area. But X and this solution here, they're incomparable. They're in no particular relationship because one is not better than the other. But as soon as I have a solution down here, this is dominated by X, and only then we can say, hey, this is actually a worse solution than X. That's the only thing that we can say. But everything else here, everything that does not sit here in this volume behind it, as defined by the fitness functions, it's dominated, so we cannot do it further. Lantian is asking, the Pareto front, so the solution, because X is now defined to be on the Pareto front, it cannot be further improved. Keep in mind, sorry, I should have said this earlier, the Pareto front is a set that in advance you do not know. You have no idea what the shape is, you do not know where it sits. Your goal is, it's like finding the global optimal solution. For many design problems, there might be one global optimal solution. here we typically have a multi-objective optimization set, but we do not know where it sits. We do not know how far we have to move away. So here, this line here is just an imaginary line. We want to find it. We want to get as close as possible. But the fact that we don't get there, well, we simply, for many real problems, we do not know where it sits. And if our algorithm gets stuck, we do not know whether it's stuck at a local optimum. So there are even multi-objective local optima. So the actual optimal solution might be over here. So we might simply get stuck and not be able to push it further. Right. So the Pareto front is essentially the equivalent of saying, okay, we are not looking at a single optimal solution, but at the trade-off set of optimal solutions. In a realistic problem, yes, just monitoring the chat, yes, it's definitely correct. Well, we can define this edge or this front here. It's defined by on an abstract way by going via the trade-off property. So we cannot improve x. Well, we can improve x to the right. So we can increase the f2 value, but it comes at the cost of some f1, for example, assuming that there are no solutions in here. So we can technically not improve x here because it sits on the Pareto front in both objectives. Good. All right, slightly more formal, and we are almost finished for today. So a more formal definition, we have in multi-objective optimization, either we have one function that maps a solution to an objective, or we have simply for m objectives, we have one function that maps, well, it might be a graph structure, but let's just say a vector of numbers to, well, an n-dimensional space. It can be 2 dimensions like we had before, it can be 3 or 5 dimensions or 10 dimensions. And in there we have this concept of dominance. So in brief, so this is the full definition. So we have to start with a weak domination. U weakly dominates V if and only if U is better than the other one, better or equals than the other one. And for a strict domination, it has to be strictly better in at least one. So it cannot be on top of the other solution. And you look at here, I'll briefly go back here. The x and something here on the that's on the same line here would be dominated. If it's on the same on the very same solution, it would not be a dominated solution. So if x and let's say y would be right on top of each other, which technically can happen, even though the underlying solution is defined slightly differently. Good. Okay. And the goal of multi-objective optimization is to find this Pareto front, or to get as close as possible at least, but we don't know when we found it unless we have artificial problems or very well-defined problems. Yeah. We'll have some exercises on this and a little bit more information on this later as well. Later in the course, not today. So for today, just a super brief introduction that the concept of multi-objective optimization exists, and that we have to think about this in a very different way, because we have the problem that, well, we have solutions that are sometimes incomparable, like X and the one here on the right, and are solutions where we have a very clearly cut dominance relationship. There's more information on the slides. This is for you to look at. I will briefly jump over, so we're here at slide 116 at the moment. I will upload the current slides later today, but it's essentially the same deck that you have already online. In a nutshell, again, let me briefly summarize the entire almost 1.5 hours or almost 2 hours now. Today, this was the introduction to search-based software engineering, which simply sits here at this intersection of search or optimization, not necessarily search-based, but optimization and software engineering. It's typically search-based. And in order to approach or formulate something as an SPSE problem, we need a representation of the solution, which often comes directly from the raw data, and we need a fitness function, which often is the result of a property that you're trying to optimize, or a metric that you have anywhere. And you can feed this into these two components into a general purpose approach like random search, local search, simulated anything or genetic algorithm, or maybe even do some multi-objective optimization. Good. That's in brief everything for today. Have a look at the additional examples that are on the slides. Learn a little bit, read, spend some time, start with assignment 1 individually, right? Keep this in mind, do the quizzes. You have until Friday, which is plenty of time. That's it from my side today. Maybe last thing is there's a question from Suman Fu. It's the same dimensions M and M, so this was, no, they don't have the same, they do not need to have the same dimensions. So for example, the 1 million test cases, so that's technically 1 million dimensions, depending on how you see it, but it can map into a single objective, into 2 objectives, 3 objectives, 4 objectives. Sharon asked, are we going to discuss the assignment? Well, not really. If you have general questions, you can ask on the forum. We will not have progress presentations for assignment 1. For number 2 and number 3, we will have, because these are group assignments. Number 1, because there's a high risk of them directly providing all the answers in the progress, in a feedback session, or before the submission. So we will not have this. If something is unclear about the assignment, go ahead and ask on the forum. This way we can help everybody. There will be a lot more information on this related to the assignment next week and in the following week. Next week, keep this in mind, please. Monday is a public holiday. Good. All right, I've seen a couple of questions, and this was excellent today. Please keep doing this. This makes the interaction also for me, or my experience, a little bit more interactive. Otherwise, I'm just talking here to the computer. So please keep doing this, and I'm hoping to see many of you again next week on Wednesday. As always, if you have questions, please ask them to the forums. Cool. I'll stop the recording now. Thanks very much. I'll upload the recording. It probably takes an hour or 2 for everything to be processed. All right. See you all later. Thank you. Bye-bye.